Hi everybody, today we're going to do an introduction to absolute extrema by looking at graphs. And let's start with something real. Here we have the spot price of Dubai crude oil from 1973 to 2024. And you might notice there are several points where the price goes up, then turns around and comes down. Those local peaks are what we've been calling relative maxima. There were also price drops that turned around and increased again, which we would call relative minima. These points are important, but they're only the highest and lowest compared to values nearby. They're not necessarily the highest or lowest of the entire graph. If you were analyzing oil prices, you probably wouldn't care about these small peaks and dips along the way. You'd want to know when was the oil most expensive and when was it the cheapest. In our graph, we can see the cheapest happened in 1973 and it was $2.83, and then the highest over this time period was $109.06, which happened in 2012. These absolute extrema are the values that matter most in the big picture. Our definition for absolute maxima says if f of c is greater than or equal to f of x for all x in the domain of f of x, then f of c is called the absolute maxima. For absolute minima, if f of c is less than or equal to f of x for all x in the domain of f of x, then f of c is called the absolute minima. So the highest number is the max and the lowest is the min. Let's take a look at that in a few graphs. In this first one, we have a parabola. We can see we have a lowest point at 0, 3. We would say the absolute minima of 3 happens at x equals 0. We know this is the minimum because on both the left side and the right side the function is going up. In this particular case, because the left and right only goes up, we won't have an absolute maximum. In our second graph, we can see we have an absolute maximum of 2 when x is equal to 0. This time the right side and left side of the graph goes down. As it goes down, it doesn't go to a lowest point, so we say there's no absolute minimum for this graph. In our next graph, which is the graph of f of x equals x cubed, we can see the function is only increasing. On the left side, our values go down to negative infinity, and on the right side, values go up to positive infinity. We don't have a lowest point, we don't have a highest point. So there's no max and there's no min. But we could have an absolute max and an absolute min if we restricted the domain of this function. In fact, we have a theorem to help us with that. The Extreme Value Theorem says a function that is continuous on a closed interval AB has both an absolute maxima and an absolute minima. The absolute extrema will occur at either an endpoint of the interval or a critical point of the interval. So if we take our previous graph and only look at the closed interval -1, 2, we can see that we have an absolute maximum at 2, 8, which is the right endpoint, and an absolute minimum at -1, -1, the left endpoint. This particular graph doesn't have a critical point. So let's look at a second graph. This time, to find the absolute extrema, we need to look at the endpoints and the critical points of the interval. Our endpoints are -3, 3 on the left and 4, 5.33 on the right. We have a critical point at -2, 5.33, and +2, -5.33. We have two highest points in this graph, the one at -2, 5.33, and the one at 4, 5.33, which tells us we have an absolute maximum of 5.33 that occurs at both x equals -2 and x equals 4. We only have one smallest point, which is 2, -5.33, which we call the absolute minimum. As we move on to look at this algebraically, I want you to remember that the absolute max or absolute min doesn't have to happen at a critical number. It could happen at the beginning or end of our closed interval. So when we move to algebraic functions, we'll follow the same idea. We'll find critical numbers by using derivatives, and then we'll also check the endpoints of our closed interval.